As we already know, the main topic covered in the chapter on integration is how we find the area under a curve. That's the big idea. That's the big picture of what we're trying to accomplish. And when we begin this chapter, you'll probably recall that we don't jump straight to finding the exact area. What we do first, in fact, is we find an approximation to that area under a curve using Riemann sums. You might remember that video, or where we make these rectangles, and then we fit these rectangles under the curve and then add up their respective areas. And that was good. It gave us a good approximation to the area under the curve. But then we discovered this great way to find not an approximation, but the exact area under the curve, called the fundamental theorem of calculus. It's a great theorem. Here's what it says. It says if you want to find the exact area under f of x on the interval from a to b, we would write this as the integral from a to b of f of x dx, and then the theorem says that you can get this exact quantity, not an approximation, by finding little f's antiderivative and then plugging in b and then plugging in a and then subtracting those two. It's a great idea. It works awesome. But then students typically have this question, usually every semester. Matter of fact, I just got it this week from a student. They say, well, Devin, if we now have a way to find the exact area under the curve, why did we spend all that time looking at approximations? Wasn't that just a waste of time? Why could we not have just fast forwarded to the fundamental theorem of calculus? And that's a great question. Why would we not? Why do we take the time to study approximations at all? It seems pointless now. Why rely on an approximation, if we can get the exact value? Well, here's the issue. Here's the issue here. This only works, this right here, this idea, the fundamental theorem of calculus, only works if you can really find the antiderivative for your function. Not all functions have an antiderivative. And so, here's an example, right? Here's an example. This is kind of a classic example that's shown in a lot of different calculus textbooks. The integral from something to something, doesn't really matter what, we'll just go 0 to pi, of sine of x squared. So here we have the area under sine x squared from 0 to pi, and I'm sure that if you graph this guy, he would have a certain amount of area under sine x squared on the interval from 0 to pi. So here we go. We're going to try our fundamental theorem of calculus. Here's our little f. So you're looking for the antiderivative, and you're thinking, okay, what integration rule would fit this guy? I don't see anything immediately. Maybe a u substitution. That would be probably our best bet. But if we let u be x squared, so we'd have sine of u, then the du is 2x dx, and I don't have a 2x, and I can't fix an x. I can fix constants, but I can't fix an x. So there is no way that this is not an integrable function. There's no way to integrate this guy, or at least a very, very straightforward way, at least, of integrating this guy to where we can plug in pi and plug in 0 and subtract. I know it has an area, but I can't find it by the fundamental theorem of calculus. That's a very limiting thing. And so sometimes we have to go back to those approximations. If there's if there's no antiderivative that we can find, we have to rely on an approximation. So you say, okay, all right, I'll buy that. That sounds reasonable. But we actually want to go a step farther than that today. See, the rectangle idea was good, and it was pretty straightforward to learn, and it wasn't too difficult. But you see, the rectangles give lots of error. And if you're going to make me rely on an approximation, I really want it to be a good one. Now you say, well, Devin, I remember how to make the approximation better. We'll just use more rectangles. Don't use 4 rectangles like you've shown. Use like 40, Well, here's the problem. I don't want to find the area of 40 rectangles. I don't want to find the area of 20 rectangles. So surely there must be a better way to get a good approximation without killing ourselves on the algebra and find the areas of just tons and tons of rectangles. See, the underlying problem behind rectangles is their jagged edges. They can only be straight vertical or horizontal. They can't be slanted and follow the function. That's kind of the underlying issue here. Well, the good news is we've got a better way to do approximations other than with these left-hand sums and right-hand sums using rectangles and whatnot. It's called the Trapezoidal Rule. It's a great approximation technique. And this is the approximation technique we should use if we're trying to find the exact area under a curve, but really can't do it because the fundamental theorem of calculus doesn't work if you can't find an antiderivative. So this would be good for something like sine x squared that you can't integrate. So here's the way it goes. Trapezoidal rule. The name pretty much says it all. We're going to use trapezoids instead of rectangles. So watch here. I'll draw it on your graph here. So what we're going to do is partition our interval the same as if we were going to do rectangles. But on each subinterval, rather than coming up and just making a flat line straight across, we're going to let each x value go all the way up to the curve and touch, and then we're just going to draw a line between them. So what we end up with is a trapezoid. Sorry for that bad drawing. A trapezoid instead of a rectangle. Now if we do this for all the different intervals, let me just do this real quickly here. If we do this for all the subintervals, then look how fantastic this approximation is. We have, still 1, 2, 3, a mere 4 trapezoids, but look how little error we get. Now, is there some error? Yeah, there's a little bit. It's right here, and but it's so minuscule, it's so minor, you practically can't even see it. And this plays out in the algebra as well. We're not going to do an example in this video, but in our next video where we do an example, you'll see just how good these approximations actually are. Okay, so now let's figure out how to do this. What is the area of just a generic trapezoid? You may have seen this in high school at some point, but in case we didn't or in case we've forgotten, here's how we do it. It's actually quite simple. We're actually going to turn this guy into a rectangle. If you look at the lowest point and the highest point, because this is a linear top here, if you take the average of those heights, so the highest y value and the lowest, and find the y value in the middle, if you were to draw a rectangle with that average height, then look how the geometry plays out. Notice how you get a little area too much and a little area too little, and it's precisely equal. So if you thought of, this is the way I visualize it, spinning this part around and filling in the missing area, it actually makes a rectangle if you kind of cut that triangular part in half, or so to speak. So the area of this guy will be the width of the trapezoid, just like a rectangle, but the height is not the lowest height, it's not the highest height, it's the average height of the trapezoid. So that's how we find the area of one trapezoid. Right, now, how do we put all this together? This is the part of the video you might have to rewind a couple of times because I might go through this somewhat quickly here just for time's sake. But the area will be this, right? So we're going to take a summation, which means we're going to add up, in this case 4, but in general n trapezoids. So let's take the sum I equals 1 to n, where we'll have two parts. We'll have the height and the width. Now the width of each trapezoid, you'll recall this from Riemann sums, we're going to call that delta x. That's the width of each trapezoid. Now the height is going to vary depending on what subinterval you're in. So here's how we're going to notate this. We're going to call this starting point x sub 0, your starting point. Now that x sub 0 will be wherever your starting point. Mine happens to be starting at 0, but it doesn't have to be. Okay, this is x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, however many you have, up to x sub n is your last one. So you have your first, your second, your third, fourth, fifth, sixth, up to your nth trapezoid. The nth trapezoid is the last one. All right, so here we go. What's your height or your average height of the first trapezoid? Well, we would add up these two heights and divide by 2. So we're going to add up these two heights and divide by 2. So now what is x sub 0? And so this is f of x sub 0 and this is f of x sub 1. So what's the average height based off of these? Well, it will be f of, all right, watch me here very closely, x sub I minus 1 plus f of x sub I. Now let me clarify that. If your I is 1, in other words, if you're in your first trapezoid, you're going to take f of x sub 0 plus f of x sub 1. If I is 1, that's your first trapezoid. Now, what about the second trapezoid? Well, the I is 2 if you're in your second trapezoid, and you'd be averaging f of x sub 1, that's 2 minus 1, x sub 1, plus f of x sub 2. So these heights, you're averaging those two. And so on and so forth, up to the last one. What happens when you plug in n? You'll be averaging f of x sub n minus 1, that's this height, plus f of x sub n, that's the very last height, over 2. All right, now, in a practical example, if we were going to actually work one of these, in all likelihood, we wouldn't write the summation notation. We would actually write them out. So this is going to be kind of long, but just go with me for a minute. I tell you what this will make this a lot quicker if you don't mind. This delta x doesn't depend on I, so if it's okay with you, I'm going to pull the delta x outside the summation. Okay, because they'll all have that same width. If they all have a half times blank, a half times blank, a half times blank, we can factor that half out, for example. So I'll pull that out. So let me just write these for each individual term. All right, if I is 1, we'd have f of x sub 0 plus f of x sub 1 over 2. And then we'll add to that f of x sub 1 plus f of x sub 2 over 2. That's for the second trapezoid. Plus, and then on and on and on again, up to, and then what's the very last one? It would be f of x sub n minus 1, the next to last y value, added to the last y value, f of x sub n, all divided by 2. Okay, so we have this pattern here. Now, if you look carefully, notice how every one of these terms has a factor of a half. They're all divided by 2. So why don't I pull that guy out as well? Okay, so I'm going to make a fraction out here. Now, let me actually write down the formula for delta x. If you recall from a previous video, how do you find the width of each of these subintervals? Well, it was b minus a over n. The b minus a found out how long your interval was, right? This was b minus a. So you take the length of your interval, and then you chop it into 4 pieces, or in general, n pieces. So now this is delta x, what I've just currently written. Now if you factor out a half, we would bring that 1/2 out, and in effect you'd basically just have 2n instead of just n. Okay, so now what's left when we pull out the 2? Well, you'd have f of x sub 0 plus, now pay careful attention to this next part here. All right, look at my cursor in red here. Here's an f of x sub 1 plus here's an additional f of x sub 1. So you actually have 2 f of x sub 1s. Now, how come? Why do we have 2 f of x sub 1s and only 1 f of x sub 0? Well, notice once you get in the middle of the problem, take a point like this, for example. Notice he's the right endpoint of the first trapezoid, and he's the left endpoint of the second trapezoid. So he's doubled up. You actually use him twice, as well as use this guy twice and use this guy twice. Now let me ask you a question. Do we use this guy twice? No. He's only the left endpoint of the first trapezoid. And do we use this guy twice? No, we only use him once as well. He's the right endpoint of the very last trapezoid. So you have this pattern of 1, 2, 2, 2, 2, 2, 2, 2, 1. And so that's important to remember as well. So we'll put ... up to 2 times f of x sub n minus 1, and then plus only 1 copy of f of x sub n. So this guy's job is to approximate the area under f of x on the interval from a to b, and he does a fantastic job of it. I'll do an example in the next video coming up here, and I'll illustrate there just how good this approximation is, because you get so little error as you move across your interval, because the tops of these trapezoids are following the curve here. Now, just in closing, just a couple of things to remember as you work through some of these examples. I've seen all the mistakes that students make, and here's just a couple common mistakes that students will make when they're doing trapezoids. First and foremost, you have to remember this pattern of the coefficients. It's this 1, 2, 2, 2, 2, 2, 1 pattern. And so you don't make all the coefficients 2, you don't make all the coefficients 1. The first coefficient is 1, but then all the intermediate points are 2 because they're left and right endpoints of the trapezoids in the middle, and then a 1 on the end here. That's one common mistake. Another common mistake is people will forget this 2 out here. Because remember, these were all averages before we factored out the 1/2. So don't forget that 2 as well. It's not just the width. This part here is just the delta x. But you also have to remember this 2 that comes out here from pulling the 1/2 out. So try a few examples of these, and if you want to go ahead and fast forward now to the next video, we'll give you an application of this. We'll actually work through a trapezoidal rule example.